Welcome back. Welcome to week 7. My name's Jason, and this week's topic is pump theory and operation. Tonight in this video, I want to cover a couple of ideas that people seem to struggle with in the pump theory and operation topic, specifically cavitation and pump head. Also, I want to give you a heads up that this week there's going to be a video coming out midweek with a guest speaker, Zach Robinson. All right, so this week we start talking about pump theory and operation, and we introduced this idea. Actually, we did touch on it a little bit before, of how we measure pump performance using a term called head. It's a little weird, right? Because why don't we use pressure? Why don't we use velocity? Why don't we use the things that when I go to the plant and I'm taking rounds out in the plant and I'm looking at the stator cooling water system, I'm going to look at the stator cooling water pumps and I'm going to read out a discharge pressure and a suction pressure, and it's going to be in pounds square inch gauge. It's not going to read in feet of head. So that's a little weird, right? Well, only until you realize that the pump manufacturer actually doesn't know what the pump is going to be used for. So worldwide, they had to come up with an idea of how are we going to measure the performance of a pump so that we can sell it to people that might use it without having to design a pump for every type of fluid you could possibly imagine, right? When I was in the Navy on submarines, we had these charging water pumps, and they were big 3-piston positive displacement pumps. Well, it turns out these are the exact same pumps that they used to pump ketchup in a ketchup factory. So when they pump ketchup, this pump has the same design. It's the same exact pump, and it has the same manufacturing design criteria, right? And so as long as you know what you need from that pump, you can say, yeah, that pump's going to work for me. And the pump manufacturer doesn't care whether you're pumping water or whether you're pumping ketchup. Same with the stator cooling water pump, right? Just because we use it for water at some specific temperature doesn't mean that somebody else isn't going to use it for something different. Using it for different fluids gives it different operating parameters, right? It'll be different temperatures, it'll be different pressures, it'll be different velocities. So they needed a way to talk about what are the capabilities of this pump and what units. And the unit they came up with was head. So head is a common way that anybody can use to determine this is the pump's ability to convert kinetic energy to flow energy, right? And that might be, that flow energy might be pressure, or it might be velocity. What you're going to learn this week is there's a pump operating curve, and that pump operating curve, the more velocity the pump is putting out, the lower the head on the pump, right? And then the less the pump is putting out, the higher the head. In fact, one of the best ways to visualize a pump's capability to do work as measured by feet of head is to imagine a pump with a pipe right on the discharge that's perfectly horizontal. When I turn this pump on, it's going to, we'll imagine an ideal system, and it will max out its velocity, right? It's going to have a maximum feet per second of this whatever fluid we're going to pump. But let's say this discharge pipe is really long, and the pump's on a pivot, and I'm able to slowly turn that pipe and then pump and point it slowly upward. So as I move it up off of its level, the velocity of the fluid is going down because it's working up against gravity now, right? And the discharge head, or in fact the pressure, the discharge pressure of that pump is going up. Okay, but there's still flow. And then I keep moving this pipe and pump, I tilt it up further and further and further until that pipe is straight in the air. Once it's straight in the air, that fluids, there's no more fluid moving, right? The pump's just spinning. It's pumped a fluid to a maximum height. Like that's as much energy as it can convert. It is converting as much kinetic energy of the impeller to flow energy, but there's no velocity of the fluid. Velocity is zero. There's no flow because the pipe is straight up, which means all of that energy has been turned into a height of a column of liquid. And that is how the discharge head is measured. Whatever that height is in feet is the feet of head that that pump produces. And what's really cool about this is it doesn't matter whether it's pumping ketchup or alcohol or water, bleach, it doesn't matter. It's going to pump whatever fluid you put at the suction of that pump to that same discharge head, that same height. So what's different? What's going to be different between pumping ketchup and pumping distilled spirits or water, right? Well, it comes down to the density. The densities of each of those change the pressure, discharge pressure. So when you think about your units, right, a feet of head, all you have is feet. And when you remove density, when you think about pressure, right, pounds force per inches squared, and you remove, you take out the gravitational constant, so you work from pounds force backwards to pounds mass, and then you take out the density. You take out the density of the fluid, the only unit you're left with is feet. So it's like working backwards to come up with the simpler unit and taking density and gravity out of the equation. Those two things don't matter anymore, and it's just discharge head. Feet of suction head, feet of discharge head, total head of that pump. That's what it's designed to do. So what's different is when you do have fluids of different densities, they will have different discharge pressures, because your actual pressure cares about the density of the fluid and it cares about the gravitational force, right? So when you work those back into it, now you have a discharge pressure, pounds force per inches squared, PSIG. And there's four real ideas with the head of a pump. Your discharge head is from the discharge of the impeller to the discharge, the pipe, right? And if we use our analogy that's pointed straight up in the air, whatever that discharge head is. And then as the pipe goes down, it has other restrictions in the discharge that add resistance to flow, and the more resistance to flow there is, of course, the lower the velocity and the higher the discharge pressure. But then there's also suction head. Now on the suction side of the pump, we also have flow energy, right? Now that flow energy may not yet be actual flow. It may not be a pump that's providing flow to the suction of this other pump. Sometimes it's just a tank. So that's really static potential energy. The more energy you have on the suction of a centrifugal pump, the more total head that pump is able to produce, right? So the total head is your suction head plus your discharge head, unless it's not. And what I mean is, if your suction head is not a tank that's above the pump level, but a tank that's below the pump level, then this takes away from your discharge head, right? Because now the pump, your total head from here to here, this suction head that's below the suction of a pump is working against what the discharge can do. So you can either help the pump by putting the suction, your suction source higher, or you can hurt the pump by putting the suction source lower. Sometimes we can't help it. My property out in Minnesota, I got a well, and it's a centrifugal pump that pumps from the ground, right? So a source below it, and it pumps it up. So the pump is designed to work against that negative suction head. We see it a lot at reservoirs. Hey, we got to pump water from a lower reservoir to a higher reservoir, or we got to move water from one location to another. Water towers. Water towers are a great example, right? We have water in the ground, we're trying to get up into a tank, and so if that's negative suction head. So when they pick that pump, they have to pick a pump with a discharge head that's large enough, high enough feet ahead to overcome that negative suction head for however far it's got to pump the liquid up to the pump in order to then pump it up to a discharge head. The ideal situation is like an aquarium pump or anything where you have a swimming pool or something where you can mount the pump lower than the suction level, because that pressure is going to work to your advantage. So that's suction head, either positive or negative, discharge head, and then total head, which is the suction head and the discharge head. Net positive suction head is how much suction head does the pump need or have available to it to prevent cavitation. Because what can happen is, if this pump is designed to pump to whatever, a 100-foot discharge, right? 100-foot discharge head pump, and it requires 30 feet of suction head, but for whatever reason, I'm pumping water that's too hot, or the tank level's too low, and there's not enough pressure on the suction of that pump, then the pump is going to start to cavitate, which is my next topic. And that cavitation damages the pump. So we have to measure how much suction head is available above and beyond that point of cavitation, because we want to prevent cavitation in a centrifugal pump. All right, so let's talk about cavitation. I feel like I wandered a lot there. I'm shooting this video a little differently tonight. Last time I went through a complicated, spent 4 hours writing a script, and I had a little teleprompter, and it was actually took longer to edit that video than just winging it. So I'm back to winging it. We'll see. Cavitation. Cavitation is impingement on the surfaces, the interior surfaces of the pump, on the impeller. That impingement is damage that destroys the pump, right? It doesn't work as well as it should, and can eventually eat away metal even. So what is cavitation? Well, if you've been boating and you've seen a propeller in the water, the propeller churns up little bubbles, right? And you see it in the movies. You see it in the submarine movies, Hunt for Red October or whatever. And the propeller's going through the water and all these bubbles are trailing off the prop. That's cavitation. Cavitation is vapor bubbles. Now, it's different than boiling. Boiling is heat is added to a fluid until the vapor bubble forms. Because it's at saturation pressure, right? It's at saturation temperature for that pressure. And then that bubble goes up, and either the whole fluid's at that temperature and the bubble can go all the way to the top, or just the bottom of that pan is at that temperature and the vapor bubble goes up and then collapses. The collapsing of a vapor bubble is the cavitation. But once again, the difference between boiling and cavitation is that with boiling, we're adding heat for a given pressure. If I'm boiling something in my pan, I'm heating the water up to 212 degrees Fahrenheit, because that's the saturation pressure, saturation temperature for atmospheric pressure. With cavitation, we're not messing around with the temperature. Temperature is whatever the temperature is. What we're messing around with is the pressure, and we can lower that saturation pressure, right? As the pump's spinning, the suction of a pump, the reason a pump works is because pressure is lower at the suction, which draws fluid in. Well, if there's not enough fluid there, or it's the pump's running spinning too fast, then it can lower pressure below the saturation pressure for that temperature. I hope that makes sense. And once that fluid is below saturation pressure for that temperature, it's now effectively boiling, but the only difference is we didn't add heat, we just lowered pressure. So it's now boiling, and those bubbles start moving through the pump a little bit, and a pump adds pressure, right? Where it's converting kinetic energy of the rotor to flow energy of the fluid, and that pressure, the discharge pressure on the pump, is going to be higher than that saturation pressure. And so those bubbles are moving through, and then they collapse. Now when a bubble collapses, if it collapses in the middle of the fluid, it just collapses uniformly, no issue. But if it collapses near a surface, right? If this bubble's cruising along here and it collapses right next to a surface in the pump, then the forces that are acting on that bubble are uneven. And what it does is it creates little microjets. And I will add a paper I read. I was looking for what kind of numbers, right? I've heard numbers like 100 times, 1,000 times higher velocities, increased pressure, whatever, right? I'll load that in there, but I'm going to go with the at least 100 times the pressure. So if it's at 100 pounds per square inch, then it can create that micro bubble. The collapsing of a micro bubble can create a pressure 100 times 100 pounds. And that collapsing bubble, right, it impinges on the surface of the impeller and erodes it away. Now, cavitation doesn't just happen in pumps. In fact, you're going to find some really cool images if you Google cavitation and dams. Anytime you have moving fluid, and for whatever reason, whether you're sending it through a venturi or down a slope where velocity goes up, pressure goes down, right? So a dam, the Grand Coulee Dam, the Glen Canyon, oh, that was a big one. The Glen Canyon Dam, let's talk about that one. They have these spillways, and the spillway, they have water that shoots down the spillway. Well, way back in the 40s, they were designing these dams with spillways that were super steep because they didn't, they're like, it'll be fine. Well, the surface of these spillways has micro imperfections on it, right? It's not a perfectly polished surface, and so it causes some turbulence. And any of that turbulence, as the fluid is moving over it, think of it as one half of a venturi, right? If I've got a bump and this fluid's moving over it, the fluid speeds up and pressure goes down as it passes over that micro bump. And as you get more and more of those, you're inducing higher velocities, lower pressures, and eventually you get some little tiny bubbles forming as the water's coming down, and then the bigger bubbles, and then more bubbles, and then you get bigger bubbles. And eventually, when you're going to come down to a part on that spillway where it starts to level out, and that means the velocity of the fluid's going to go down and the pressure's going to go back up. And so those vapor bubbles or vapor bubble are going to suddenly collapse. And all that 100 times higher pressure is going to impinge. And you'll see pictures, I think it was the Glen Canyon, it was like 13 meters wide, 8 meters deep, something like that, one of the dams. I'll find some of the examples and load them into the module. But yeah, it's incredible. It's incredible how much damage can be caused by cavitation. So again, I just wanted to cover those two topics real quick in this intro video. The idea of pump head. Why are we suddenly using this term? What does it mean? Why not just talk about pressure or velocity? Well, because it doesn't help us. It doesn't help the manufacturer. It's a nice, simple unit. It's just feet. We don't have to worry, we don't have to worry about density. We don't have to worry about any of the other things. It's just, this is the pump, and it will take whatever fluid you put at the suction of it and pump it straight up to that height. If it's an 80-foot head discharge pump, it'll pump any fluid, ketchup, alcohol, whatever, to 80 feet. And then cavitation, of course, we are worried about not just the discharge of the pump, but also the suction of the pump. We have to make sure that we're not going to cause cavitation and destroy this pump, because pumps are expensive. They are a little fun to rebuild. My time in the Navy as a mechanic on submarines and mechanic in the engine room, so for nuclear power plants, I got to rebuild more than a couple pumps. And again, we're going to have a guest speaker this week to take you through the rest of the material. I may be a little late getting the rest of the stuff uploaded this week. We'll see. If you have any questions, let me know. I hope you have a great week. Before you can understand why cavitation is, no, that's not it.